if you're thinking, what is this device doing? You're in the right place. So this is a rain gauge. It measures how much it rains. And I will explain you how it works and how you can build one for yourself. All right. So this is the 3D model of the rain gauge. As you can see, this was designed to be 3D printed, so it's splitted in multiple parts. The diameter of the bucket it's 180 millimeters, so you can actually calculate how much water it can accumulate during the rain. So you can calculate the rain height in millimeters. So that's a pretty basic mathematics, so you can calculate it. Let's hide a couple of parts. So let's hide the ring because I'm not gonna need it here. As you can see, it has a filter inside, so it can filter debris like tree leaves and some other, junk that can be stuck in the small hole and prevent water from getting inside the sensor. All right, so let's hide this one as well. The bucket itself, it's transparent, but I'm still gonna hide it so we can, not the bucket, the can. All right, so this will give us the preview of the inside mechanism. It's made out of a bucket, so the green thing is the bucket, which can accumulate a certain amount of water. The maximum volume of the bucket itself it's 10 milliliters, but it might swing differently depending on a couple of variables, like friction between the parts. So friction can affect how much water can be held in the bucket until it swings. So the movement is something like this. If I put the movement point here and just rotate the part, it will swing like this. So water drops from the top. So it drops from this small hole, and the bucket will actually swing, right? It will swing. And the other bucket will get filled as well, and it will swing in the opposite direction. So it's a movement like this. All right. Okay. This box, it's inside the sensor. It's just for protecting the electronics. The main thing for this rain gauge, it's the sensor type that I used. So initially this was designed for a read relay. So it has a read relay and a small magnet. It can be done with a Hall sensor as well, and probably with an optical device like an encoder or so. So there are many options in order to detect the swing of the bucket. The best option that I was able to find is to use an inductive position sensors, which doesn't use any type of magnet. It's very robust to interference, so it won't be affected by magnetic field or temperature differences and so on. Let's hide this box so I can reveal the sensor itself. The cap as well, I don't need it. All right, so we have this axle, which can be either plastic or metal. It can be made out of metal as well. The axle is fixed to the bucket, so if the axle moves, the bucket will move as well. And also this piece of plastic, so that the axle goes through this piece of plastic. It's not getting all the way through, but maybe around this area. So the holder for the target gets attached to the axle. And on the top of the target holder, you actually glue the target, which is made out of PCB. All right, and The sensor itself, it's this green PCB. All right, between the PCB, the sensor itself, and the target, you might have, or you will have a certain amount or air gap. So it will be a small gap between these parts, between these two parts. It is required so you don't have friction between the sensor and the target, which will affect your measurement. So I would say distance of 1 millimeter should be okay. It will give you good readings from the sensor. All right, so let's discuss a bit about inductive position sensors. So what is an inductive position sensor? So you'd say it's something that measures the position. Yeah, but how it does the measurement for that, it's pretty amazing. And the most amazing thing about Microchip inductive position sensor is that they measure movement without using a magnet. And as you might know, magnet is expensive, it's hard to find, and it's not energy efficient to manufacture it, right? And it's also natural resources that might or might not be available. All right, so instead of using a magnet, it uses a set of PCB coils and a simple metal target. A transmitter coil, like this one over here, the primary, generates a high frequency magnetic field, which creates, of course, eddy currents in the metal target. As the target moves, like I'm showing in this animation here on the Microchip website, those currents change the magnetic field, and the two receiver coils, secondary cosine and secondary sine, generates the sine and cosine signals, right? And of course the LX part, in this case 3302, processes these signals using 8 tangent to function to calculate the target position with very high accuracy. And you can see in this example we have an analog output which it's proportionally to the target position. So if you rotate the target, as I'm doing right now, you have a different voltage output. So it ranges from 0 to 5 volts, right? And because it relies on the inductive coupling instead of magnets, the sensor is highly resistant to magnetic fields, dirt, oil, and temperature variation of any kind. And it's ideal for demanding industrial or automotive applications. You can also output the sine and cosine as well. So you have a SENT interface and also a PVM output. So the data cycle of the PVM, it will change with the target rotation. You can find all the 3D models on Onshape. So the project is fully open source. Also, you can find details about the software and the software file for ESPHome for Home Assistant as well. So take a look to my GitHub account as well. So happy 3D printing and building your Rainfall. I'll let you watching the build process, which is a bit longer than I planned before. So enjoy. If you like the video, please consider subscribe and just press the like button and share with a friend. And thanks for watching. Bye.